this is a one variable problem. So just remember for a second, because we need to remember the one variable process. So I have x, I have z in this case, and I have 0, and I have 3. And I'm trying to zoom in on the window and say, what's the highest and lowest it can be? A very practical question. I don't care how many bumps there are. I just want to know what the biggest value is and what the smallest value is. That's what this question's asking. Sometimes we call this the absolute maximum, sometimes we call it the global maximum. We use those words interchangeably. Okay, so here's what you do in one variable calculus. You have step 1. You take the derivative. You set it equal to 0. That's what you always do in calculus if you'd forget what to do. Use the same strategies we've been using for many variable calculus. You factor if there's any way to factor, if there's anything common. In this case, they both have a 2, they both have an x squared. You get 9. So this is just going to depend on how good you are with your Algebra and Calculus 1 skills. That's a big challenge in this next piece of the course, but that's sort of always there. And the only way that can happen is if x equals 0 or if x equals 9 halves, or 4.5. Okay, so that's what we get. And I'll just say 4.5. So if the question is, those are the only two places where it's possible for this function to have bumps. If your goal was to classify them, you could do second derivative tests, you could do first derivative tests, there are all sorts of methods, but that's not the goal here. The goal is just to find the biggest overall. Okay, so then the conclusion was, whatever your picture looks like, and it doesn't matter how many bumps it has, the max and min will either be at one of the bumps or at an endpoint, and that's it. So that's all you did, is you said, okay, are any of those points inside this region? And you say, well, this one's not, it's over here and I don't care about it. This one is, but it happens to already be an endpoint. And so then you just plugged in all the critical points and the endpoints, and that was it. Sometimes students say, I forget where I'm supposed to plug it in. You're plugging it into your function because you're trying to find out what makes your function the biggest. So you'd plug in 0, and you'd plug in 3. So this is just such an important method that I think it's worth me stopping and just making sure that everyone knows the one variable calculus version of this, 6 times 3 cubed minus 3 to the 4th. That ends up being, I'm going to use my 81, and then you were done. And the answer should be staring you in the face. Whatever is the smallest one of these numbers is the absolute or global min, and whatever is the largest number is the absolute max. I mean, this is sort of appeal to students. It's almost like a black box that just spits out the answer. And all I had to do was take the derivative set equals 0. My answer is sitting there, but I had to know that I had to check the critical points and the endpoints of my region. Now, if you were to graph your region, it actually looks like this. It comes up, it flattens out for a second, it goes up. Over at 4.5, it has a high point, it comes down, but the question wasn't about that. The question just is, well, what's the biggest and smallest? And the biggest value is 81. The smallest value is 0. Whenever there's a closed interval, and the book kind of goes into this, you don't need to know all this, but if it's a closed interval and the function doesn't have any breaks in it, then there always is one maximum and there always is one minimum. And it always is either at an endpoint or a critical point. That was this idea. And you would say the maximum is 81 and the minimum is 0. So just like this in the homework, the value of your function is the output, not the input. Okay, so let's just try it again. So I always do this as an entry task. I mean, it's good to pause and just say, do you remember this? Every Calculus 1 student should be able to take a function, chew it up, and spit it out. Basically, in a matter of 30 seconds, tell me a ton about this, just using derivatives. So again, we're doing 0 to 3. We take the derivatives. H prime of x is 18x squared minus 18x. You set it equal to 0. You factor if you can. X minus 1 equals 0, you get x equals 0, or you get x equals 1. You go down here to your region you were talking about, 0 and 3. That's what they told me. They have to tell you that. You say, are any of those points in my region? This time they are. There's a 1. And so I have 3 points I have to consider. And one of them is sitting there. So again, to me, it's just amazing how fast this gives you the answer. And so you're going to plug in the endpoints. You'll plug in 0, which gives me 6 times 0. Okay, that's 0. You'll plug in 1, because that's one of the points you have to consider. And so it's 6 times 1 cubed minus 9 times 1 squared, which is negative 3. And you plug in 3, which is 6 times 3 cubed minus 9 times 3 squared. So the bad part is at the end of these problems, you always have a little calculation, but then the answer is sitting there. The absolute minimum and the absolute maximum is sitting there, and that's it. If you found all the critical points and all the endpoints, you're done. That's the answer is sitting there. And if you wanted to, you could graph it. If the goal had been to find out more information about the graph, then you could also have done the second derivative test and found all the pieces. This actually must be like this, and it must come up like this, and 81 is like this. It's right there. This is not to scale. Minus 3 is right here. Boom, boom. Okay, so I always do that in class. This is the day that I hand out that sheet that I showed you in live stream that says, here's a review of all our Calculus 1 facts. You need to be able to do this and do it fast, because the process of doing absolute max and min will involve doing possibly multiple ones of these problems. So later on today I'll say, now we're going to do a global max and min one variable problem, and you'll do this. If this is foreign to you, then this section is really hard. So that's why I always stop. I've learned after a couple years of teaching this that I should stop and just talk about this. But this is really powerful. Give me any function, and in a matter of a minute or two, I will tell you the max and min, just with pencil and paper. It's pretty cool. All right. So let's leave that. Now you have that. So there are some differences. Unfortunately, there are large differences in terms of computation. This is much worse computationally. So these are the biggest problems, and because of it, in the homework, they ask you it in such a way that it's manageable. You can do it on a sheet of paper. Same thing goes in the test. If I asked you a question on this, it would fit in a half a paper to a 3/4 of paper, and that would be it. So I have to be careful in how I ask these. I'll show you in just a second. There's one big difference, and it's a big one. The big difference is this. The problems we just did, there were two endpoints, an endpoint here and an endpoint here. In this problem, there's an endpoint here and there's an endpoint here. I already mentioned this back when we were first talking about chapter 14, that the biggest difference in 3D is regions. So let's say someone says, find the maximum above this box. How many endpoints are there? This is the problem. There's an infinite number of endpoints, not just two. The boundary is the problem. So if you're trying to study what's happening to this surface and you want to know the max and min, it might be somewhere on this side or somewhere on this side or some. So we go from two endpoints to an infinite number of endpoints. The concept is the same. It's either at a critical point on the inside, somewhere in the middle, a bump in the middle, maybe it's a, something like that, or it's on an endpoint. All right. So here's the world's easiest example. Why do I say that? If you were to graph this, here's x, here's y. This is a paraboloid that starts up here at 3. Actually looks like this. Here's 3. And I'm going to draw a circle of radius 2 on the ground. And I'm going to kind of shade it in. And I'm going to say, if you're standing in this region and you point up, where should you stand so that when you point up, the surface is closest to you, if you went straight up? And where would you stand so it would be furthest away? Let's find the absolute max and min. So here, I do this problem because it's the fastest in terms of setup. I'm going to go through the process. It should look like, it's actually just like what we just did. Step 1, find the critical points. You do the partial with respect to x, so you get two things. Partial with respect to x is 2x, you set that equal to 0. The partial with respect to y is 2y, you set that equal to 0. So that's, it's bigger because we're doing both partials, and then you combine. Now the only way the first can happen is if x equals 0. If I plug that into the second one, it doesn't change anything. So y has to be 0, so the only critical point is 0, 0. In the last lecture, we learned how to figure out if that was a local max and min. It turns out it is a local min, but that's not what this question is asking. So then you move on to the second step. And you figure out, is that in my boundary? Is it something I need to consider? And so on. But unlike this problem where you just had to think about a region, is my number between 0 and 3? you have to ask if your critical points are inside a region. So my picture is usually this. The next thing I do is I draw this picture and I draw the region. So it's important to recognize in these problems there's always a region. This time it's a circle of radius 2. It has nothing to do with the surface. It's just something special they gave me, right? They give you a surface, they give you a region. Okay, so now let's go. I like to just mark as I go. So I like to say there's one point I have to consider, which is 0, 0, and it's right there. It's the only point in the inside I have to consider because it's the only critical point. So that's a big time saver. Now I'm going to go to the boundary. So then we go to the boundary. Now typically what you'll do for the boundary is you'll solve for x or y and substitute it in. In this case, I can describe the entire boundary as x squared plus y squared equals 4. I could solve and say, now there's an upper half circle and there's a lower half circle if you wanted. But it turns out in this problem that doesn't really matter. But this is what I do. And then I'm going to substitute that into here and find the intersection of what does it mean to be above this boundary and on this circle. So I'm basically going to kind of go up and I want to study the edge where they meet, so to speak. That sounds complicated, but it's not. What you're going to do is you're going to take your function, whatever it is, and then you're going to substitute and replace the y or the x and get it down to one variable. That will turn into a one variable function that describes the points above the boundary. So in this case, when you do that, it actually doesn't matter if you do the plus or minus. I'll say it this way. I hadn't intended to, but I'll do it just so you get more of a feel for what it's like. Usually when you do this, you end up with a one variable function, and then you go back and you say, well, the smallest x can be, if I walk this way, is -2, and the biggest x can be is 2. Sometimes in class I'll do a buzzer. I'll say, hit the buzzer when I enter the region. And those are our bounds. So we say -2 to 2. So this turns into one of these problems. I have an interval. I have a function. I'm going to do a one variable max-min question. For every boundary, you do a one variable max-min question. So this can be big. In this case, it's like the best of all worlds, because look at what happens. You get z is equal to x squared plus 4 minus x squared plus 3. So you just get a constant 7. So I really don't need to go through and do the rest of it. Students are confused by this piece because they say, how can it be a constant? But this is saying that no matter where you're standing on this edge, the height is 7 above you. So it's just a constant 7. And then the way you finish this problem is the same way you finish the one variable problem. We've now considered every point on the boundary, and everywhere on the boundary, we're getting z equals 7. And the answer either has to be on the boundary at a critical point. So the only other point we have to consider is 0, 0, which we already found. And you do the z at 0, 0 is when I plug in a 0 and a 0, I get 3. And the answer must be sitting there. And there we go. This is the absolute min, and this is the absolute max. The absolute max occurs at many places. That's not unusual. The absolute max could occur at many places. But the highest you're ever going to get is 7. And the lowest you're ever going to get is 3 above that region. Okay, so you see the problem is the boundary. And this was not present in one variable calculus because the boundary was always just 2 points. All right, so now let's see sort of a more full-blown question. But to me, I always remember how to do this because I know the idea, right? Find the critical points, go through the boundaries, there's your answer. Okay, so you have to have a plan of attack. So this is a more formal treatment here of what we just did. Find the critical points inside the region. Find the critical numbers over each boundary. In the last question, we didn't have to do that because there was just a constant over the entire boundary. But basically, this is saying do one variable calculus above each boundary, and then plug all those points in and see what your winner is. If you want to be more formal, some students say, tell me precisely what to do. On this second step, what I mean is for each boundary, you're going to get an equation that describes the boundary. It'll typically be like a one variable something. and then you substitute that in. You also have to consider the corners, because for a one variable calculus problem, back when we did this one variable problem, you had to consider the endpoints. Okay, so we're going to do that. So the problem becomes more challenging if there are lots of boundaries to worry about. So here you go. So here's an example. There's a surface. So sometimes you can just get lost in that, what's this and this? But do remember that every one of these questions, you don't have to have an accurate picture. This is sort of my catch-all for all surfaces, and I apologize because I know it's not the right picture. But I just sort of draw a little folded sheet. That's not the picture for that, but if you're just ever trying to do this, here we go. So in every question we do, pretty much from now until the end of chapter 15, we'll have something like this. We'll have a surface that tells you the height, and we'll have a region drawn on the ground. And usually what we'll do is we'll just draw the region, and then we'll worry about kind of the surface and how that comes into play in just a second. Now this says x has to be greater than 0. X has to be greater than 0 is this side over here. And it says x squared plus y squared is less than or equal to 9. So that's a circle of radius 3. Okay, so there's 3, there's negative 3, there's 3. If you wanted to graph that here, we're talking about this. Okay, so now the question is asking this. Where would I stand on here so that when I point it up, the surface is going to be furthest away, and where would I stand so that when I point it up, it's going to be closest? And at the end of this problem, you will end up considering those endpoints, because those are going to be the endpoints of a one variable problem, along with any critical points on the inside. So now we have the plan of attack. It's not as bad as I just made it out. Let's just do it. Find the inside. So I'm going to do, are there any critical points on the inside? So I'm going to do the partial with respect to x. That's going to be 3x squared minus 12. I'm going to set that equal to 0. The partial with respect to y, that's going to be 2y. Take whichever way, either one is easier. Y equals 0. Substitute y equals 0 up here. If there's nothing to substitute in, that's not a problem. You just keep going. But y has to be 0, we know now. And then in order for this to work, x squared has to be 4. And so x is plus or minus 2. That gives me two critical points, negative 2, 0, and 2, 0. Okay, so that's the stuff that's really the partial derivative stuff we were doing in all the previous sections. Then, in this case, it's just asking me for points inside that region, so this is where I'm glad that I drew it already. This is not in the region, but there is a point right here I need to consider. I find it kind of interesting in comparison to Calculus 1. Calculus 1, the hard part was the inside. In this case, I always feel like the inside is the easier part of the problem, and the boundary is the harder part. So now we're going to do the boundary. And the issue is there's really two very different boundaries. There's this vertical line, and then there's this boundary. And I want to study the points above this side, and then I want to study the points above this side. So I'm going to give equations for both those. So I'm going to break it into two boundaries. This boundary here, let me write down how to describe points on this boundary. In order to be on this boundary, x has to be 0. And, let's do the little buzzer. Y has to be between negative 3 and 3. That's what it means to be on this side. And so now what we want to do is we want to take our surface and restrict it to just points above this side. And that's actually easy to do. You just replace x with 0, which you just found. You get 0 cubed minus 12 times 0 plus y squared. So really what I need to do is z equals y squared above this region. Then do calculus 1. Find the global maximum of that function for this one variable function between those 2 points. Do the entry task. If we don't know how to do the entry task, this becomes really hard. But the answer is take the one variable derivative. This is why I like to just write it as z. I'm going to take z prime, you get 2y, you set it equal to 0, you get y equals 0, and then I'm happily on my way. My conclusion from that is on this side, I need to consider points on this side where y is 0, so that would be 0, 0. I need to consider the endpoints, which would be this point, 0, negative 3, and this point, which is 0, 3. Okay, I'm done with that side. I like to wait and do the calculations at the end, but you could do them now. I mean, you could plug them in now. You can even see, this might be easier to plug in for that side. The things I'm going to get are 9. You could even label them if you wanted, if you prefer. This is going to give me 9. This is going to give me z equals 0. This is going to give me z equals 9. So right now 9 and 0 are my leading contenders for max and min. I haven't tried this one yet. I could have plugged that in. I'll wait a second. Okay, now we go to the next side. What if you're standing on this side? What would be an equation that describes that? Now some people go, well, it's a circle, so wouldn't we use this equation? Sort of. I mean, I would want to rearrange it in a form that's useful for us for what we're going to do. A couple ways you could go here. And I don't know what's better. You always can make a choice of how you want to substitute this in. Sometimes that choice will be based off of what you have here. Sometimes it'll be based off of your equation. You know, if you solve for y, you're going to get y is plus or minus the square root of 9 minus x squared. If you solve for x, you're going to get x is plus or minus the square root of 9 minus y squared. Those constitute, you know, the positive y's and negative y's, that's those. And the positive x and negative x, that's those. Now, the truth is we're actually dealing with the positive x's. But if I substitute and replace x, I'm going to have these square roots. It's okay, but it'd actually be easier to differentiate if I replace the y. Because if you look at that, it's going to be much prettier if I substitute that in there, because the square roots go away. That doesn't mean it can't be done the other way, but either way you have to substitute one of those in here and then make appropriate conclusions depending on how you want to do it. So what I say is the easiest way would be to plug this in. Now there might be some concern about, well, that's going to split into upper lower circle. Let me think about that for a second when I put it in. But your preference, if you want to replace y with plus or minus the square root of 9 minus x squared, you can. If you want to replace x with the square root of 9 minus, you wouldn't have to do plus or minus there because it's only the positive x, y. You can. Either way, it's going to give you a one variable calculus problem. You'll take the derivative and set it equal to 0. Let's replace the y, do the nicer of the two. So that's going to give me z equals x cubed minus 12x plus, I'm only doing this because that was a y squared. So this is going to be 9 minus x squared. Now I do have to think about this. Since I decided to do it in terms of x, the boundaries are actually this. The smallest x can be is 0. The biggest x can be is 3. So this is a corner. It doesn't look very cornery, but it's a boundary. X has to be between 0 and 3. So from the perspective of x, this is an endpoint. Okay, there's a one variable calculus problem. So how do we do a one variable calculus problem? We take the derivative. We set that equal to 0. Does that factor nicely? Maybe it doesn't. Let me just peek at my notes. I might have chosen one where the numbers... Right, yeah. Doesn't factor nicely, so you sing the quadratic formula. Negative b plus or minus square root b squared minus 4ac all over 2a. And then you get this thing. 2 plus or minus the square root of, actually I don't even think I worked it out in my notes. At this point I switched over. This is negative 12. 4 minus a plus 144 over 6. So at this point when I do this in lecture, I say, okay, I'm going to stop and just sort of we can go longer with precision, but my goal is to get this idea across and show you that it doesn't always have to be nice. So I got these two values to consider. I don't need the negative because I don't have negative x. I do need the positive, and that actually leads to 2 points here, because if x is 2.36, wherever that is, that would correspond to a point there on this side and a point there on this side, and I'd also need to consider that. Okay, so in total I would have 1, 2, 3, 4, 5, 6. I'd have to consider that because it's an endpoint or an extreme point, and I'd have this to plug in. So here's one more. There's a function. This boundary is more exciting. So that's really why I do this one. So let's just go through and see it. Let's worry about inside, step 1. The partial with respect to x is 18x squared You set that equal to 0. The partial with respect to y is negative 2y. You set that equal to 0. X has to be 0. Y has. Usually there's more, finding critical points is more involved, but when you're doing these problems, we often try to make that part easy because you already have enough going on. For the second part, I would draw the region. So, again, think of this as it is a 3D problem. There's some surface up here, but ultimately, let's draw this region on the ground. This is the region between this parabola, y equals x squared, and this line, y equals 3x. So this is where we're starting to get into, in my mind, Calculus 2 territory. In Calculus 2, you did a ton of things where you were working between regions and trying to decide whether you wanted to use x or y. Those questions are going to reappear in the weeks to follow, and we'll do lots of recapping of that. So this point is 0, 0, and this point is 3, 9. Okay, so I did a little bit of extra work on the side. That's the region. It's this unusual region on the ground. And we're trying to find out where you would need to be above it to have the biggest max and min. Okay, 0, 0 is actually a point right on the edge. It's already a corner. So there's no other points on the inside I have to consider. Nothing else came out of this. So now we're going to go one by one through the boundaries. And this time they gave us the boundaries outright. Y equals x squared. And depending on which one I use, if I decide to use x, I should say x has to be between 0 and 3. Or I could say y has to be between 0 and 9. And then once I finish that problem, I'll do this problem, which is y equals 3x. That's this side. And again, I'll choose whether I want to use x or y here in a second. And then we'll put all those things together. So I would like to study this surface above that side first, above this side. So let's do it. Let's take the surface. Let's replace y with x squared, and that will force it to be above this side. And then we have 6x cubed minus y to the minus x to the fourth. So now we're almost done. I just need to know, I know what the endpoints are. I know those 2 points. I just need to know if there's any critical points here. So I take the first, the regular old one variable derivative, 18x squared minus 4x cubed. I set that equal to 0. I factor 2x squared. Hey, this looks familiar. This is the entry task. Now I remember why I used this example. 9 minus 2x equals 0. So I usually do that entry task as part of this lecture. Because when I get here, I say, do you guys remember how to do this? Do you know this problem? And students usually give me blank looks because they're scared by that point in the lecture. And so then I do this. And I go, remember that entry task we did? This is it. We're doing it right now. Right? We're finding the maximum of this one variable function. There it is, over the interval 0 to 3. And you already told me how to do that, and we thought that was maybe kind of easy. I don't know. So we found out there is a critical point. It's at 4.5, but that's outside the region. And so the only 2 points we have to consider are that and that. And then we plug this in. And so we say over this side, we have x, and y is 3x. That would mean you're standing above this side. And so you get 6x cubed minus, if I put a 3x there, it's going to be 9x squared. And then that's when I say, hey, we just did that. That was the other entry task. And you already figured that out, that you had to consider 1 on that side. So that would give me the point 1, 3, and the endpoints. And so when all of this is done, what have we learned? I need to consider the point 0, 0, because it's an endpoint. It happens to also be a critical point. We need to consider the point 1, 3, because it's a point on this boundary that could be a max or min. And we need to consider the point 3, 9. And we need to see who wins. Who gives the biggest output? Okay, so let's see. This one gives an output of 0. This one gives an output of 6 minus 9, which is negative 3. This one gives an output of, let's see, so that's going to be 27 times 6. 6 times 27. I should use, we already calculated this. I think it was 81. So there's the absolute max. and there's the absolute min. Okay, so that's kind of a nice way to wrap things up, to basically say, yes, these are hard, but they're hard because you're having to do a one variable calculus problem. You can see that was most of the work was one variable calculus. Okay, hopefully you're starting to get the idea of how that goes.